Hello, so in today's video, we're going to look at how we can use small angle approximations to perform calculations. In yesterday's video, we looked at how we can actually use these small angle approximations to the ones that I've written down here. So when theta is a small angle, when you have a small angle, that means that sine theta is roughly theta, and we looked at that yesterday. We also looked at the second one, so when when theta is a small angle, cos theta is approximately 1 take away theta squared over 2. And again, when theta is a small angle, tan theta is approximately theta. So again, let's just be really clear about this. So if you've got a small angle, then sine of that angle is approximately that angle. If you've got a small angle again, the cos value of that angle is approximately 1 minus the angle squared over 2. And again, tan of a small angle is approximately 1 minus the angle. Sorry, not that. Sorry, my bad. Just the angle, approximately the angle. Yeah, so they're going to be the approximations, and we will need this to do the problem on the next page. So let's say you've got a question that says, if x is a small angle or small value, find an approximation for this fraction here. So the fraction tan 2x times by 1 minus cos of 3x divided by x times sine squared of 4x. So let's use our small angle approximations. So let's start with the tan one. So tan of the angle is approximately the angle. So tan of this angle 2x is going to be approximately 2x. Now let's go to the cos one. So we've got cos 3x. So remember, cos of the angle is approximately 1 minus the angle squared over 2. So this is 1 minus the angle 3x all squared over 2. And that would be equal to 1 minus 9x squared over 2. Okay, so we've got that. And then our next one is going to be sine of 4x. We've got this like sine of 4x there. So that's going to be approximately equal to the angle using the first rule there. So that's approximately equal to the angle, which is 4x in this case here. And also, I mean, we've got a sine squared as well. So let's just write this here as well, just to be clear. So sine squared of 4x, remember, this is just the same as sine of 4x all squared, that's just how the notation works. So we're doing 4x all squared, and that's going to be a 16x squared. Okay, so now we can plug these all into our formula or our fraction. So sine 2x, that becomes approximately, I put like an approximation sign here, so approximately 2x, and then times by 1 minus this this cos 3x approximation, so 1 minus 9x squared over 2 in brackets, and then divide by x times by this this thing here, this 16x squared, so times by 16x squared there. So then when we simplify all this, we will get, so in the inside of the brackets on the numerator, 1 take away 1 is just 0, and then minus 9x squared. Well, we're going to get a 9 over 2x squared, so 9 over 2x squared there. Because again, the 1 take away 1 gives you 0. Minus 9x squared over 2 is 9x squared over 2. And then we can divide this by x times by 16x squared. So actually the x's just cancel out there. And in fact, the 2 times 9 over 2, the 2's just cancel out there. So we're going to be left with 9x squared over 16x squared. The x squares cancel out, and so we're left with 9 over 16. So when x is a small angle, this number here is approximately equal to 9 over 16. So that's what the small angle approximations have told us. So that's an example of when we can use small angle approximations to do calculations. We can also use small angles in other areas of maths as well. So we've not done differentiation, integration, or differential equations yet in these series of videos. So we'll come on to those soon. But you can use these in these topics as well. So in differentiation, if you have to differentiate something complicated like this here, it's much more simple to just pretend that x is a small angle, these like x are small, and then you can use your small angle approximation, substitute that into your expression, and then you get something more easier to differentiate. And the same with integration as well. You can use your small angle approximations. You can, if you assume that x is small, you can use your small angles to approximate this, and then you can integrate it more easily. And the same with differential equations as well. So I mean, Yeah, so what I've done here, so we know that tan theta is approximately equal to theta when theta is a small angle. So what I've done here is I've just said that solving this differential equation, and in fact, in the A-level maths course, we don't need to worry about solving second order differential equations. So I mean, this is just like a random example to make the point clear. Yeah, so it's much easier in maths to solve an equation like that than it is to solve an equation like that. So sometimes you just assume that you know, theta again is a small angle, so you can solve the equation easier. So that's just a summary of how you can use these small angles to do calculations, to work out fractions, and also when we do differentiation and integration to differentiate and integrate functions easily compared with more complicated examples.